In section 6.3, we're going to be talking about basic facts about parallel lines, and we'll do so starting with a few definitions. First of all, a line and a plane are considered parallel if they do not touch. This should make sense because if they are not going to touch, they're going to keep the same distance between each other, kind of referring back to parallel lines. The second definition is that two planes are parallel if they do not touch. That is, again, kind of similar to the first definition. If I have two planes that continuously keep the same distance, they are considered parallel. Now, something that's a little bit different is that two lines are considered what's called skewed if they are not coplanar. So what that means is if I have two planes, as we do above, and this is plane X and this is plane Y, and I have a line in the first plane that could go like this, in this direction, but in the second plane, I could have a line going in this direction. Now, you can clearly see they do not go in the same direction, but they will never touch. Therefore, again, they're considered skewed. Theorem 48 states that if a plane intersects two parallel lines, lines of intersection are parallel. So let's think about what this looks like. So then if we have the blue line intersecting the red parallel planes, we can kind of see what's going on. The green line representing the intersections. So if you can see that, they continue to have the same depth apart as the planes. But since the plane cuts them at the same place, because they're parallel, the lines will continue on in the same direction, therefore being parallel. Looking at this example right here, again, we have a three-dimensional figure with two planes, plane P and plane Q. We're given that plane P is parallel to plane Q. Line segment, or AD is parallel to BE, and line segment CF is parallel to DE. And we want to prove that angle BAC is congruent to angle EDF. Now, if we think about where we're going, angle BAC is right here, angle EDF is down here, and you'll notice they're kind of part of a partial triangle. So the first thing we're going to do is we're going to draw BC and EF to create a full triangle. And we can say that because 2 points determine a line. So now we've completed the triangle. If we can now state that the triangles are congruent, then we can say that the parts of the triangle are congruent. One of the beginning things that we'd like to do, though, is we'd like to establish that ACFD is indeed a plane. And we can do that by saying two parallel lines determine a plane. And we'll do that with ABED as well, based on the same reasoning. The reason why we're going to do that is because that establishes that a plane is intersecting two parallel planes. And what that does is it helps us to create that AB will then be parallel to DE, and that line AC will be parallel to DF. And we'll do that with the third side as well, BCFE being a plane, and then BC being parallel to EF. Now, let's think about why we would do that. Well, if I know that this right here is parallel to this, And I already know that AD is parallel to BF. If you see that figure in the back, it's actually a parallelogram now because we established two pairs of parallel sides. The same can be said with the other two planes. But again, why does that help us? Well, if we remember what some of the properties of parallelograms are, we know that parallelograms have pairs of opposite congruent sides. So not only can we say that AB and DE are parallel, but we can also establish that they are now congruent. So AB is congruent to DE, and then we can establish the same with AC being congruent to DF, and then finally BC congruent to EF. And that's enough information, having all three sides congruent, to establish the triangle's congruent. Triangle ABC congruent to triangle DEF. And once the triangle is congruent, the angles BAC and EDF are congruent based on